Hello SPH3U, Mr. LaRusso here again. Today we're going to further work on wave theory. So let's start off with exactly what is a wave. So a wave is defined as a transfer of energy in the form of a temporary disturbance of a medium, where the energy of the wave travels from one point to another, but the medium itself only experiences localized motion. All right, so what is meant by that? Well, let's take a look at this example here. It's called a mechanical wave. So here's what we mean by this. As you can see, the pulse moved up. The energy is moving from left to right, but the medium itself is only vibrating up and down. So this is the concept of a wave. So the medium, which is the spring, it actually physically doesn't move from left to right, but the energy of the wave does. So what type of waves do we have? Well, as mentioned, we have things called mechanical waves. And these are most of the kinds of waves that you would experience in everyday life. And these are the ones that are governed by Newton's laws. So some examples are sound, seismic, which means earthquakes, water waves, which is self-explanatory. And all of these types of waves, and this is very important, they require a medium. And they can be both longitudinal, transversal, or torsional. We have some examples of what those things look like. The other types of waves, this one you're also familiar with, called electromagnetic waves. And now you might not be familiar with them by name, but you definitely know them by their property. So visible light is an example of an electromagnetic wave. Radio is an example of electromagnetic waves. Ultraviolet, infrared, X-ray, all of these things. These are examples of electromagnetic waves. Now, what's cool about these is that they do not require a medium. And in fact, that's because there is a more complex nature of electromagnetic waves. They actually kind of behave both like a wave and a particle. So it is kind of a BYOM, bring your own medium. So they actually bring their medium with them. And these are the only types of waves that can pass through the vacuum of space. Mechanical waves cannot. So that's why there's no sound in space. You can see because light is a electromagnetic wave, but sound is a mechanical wave. So of course, the astronauts, when they're in their space capsule, hear sound because the space capsule is filled with oxygen, with air, and has an atmosphere and the waves can pass through. However, if they're out on a spacewalk and they have their own contained suits, they could not talk to each other unless they had radio communication, because there's no way for the sound to go from one suit to the other because in between them is the vacuum of space. So electromagnetic waves, they kind of, well, obviously we can't really look at them, but they have two parts to them. And one part is the electric part. So these are varying electric fields going from like a positive to a negative voltage. And perpendicular to that, they have a magnetic field. And that's why they're called electromagnetic. So it goes from a north pole to a south pole to a north pole to a south pole. So the cool thing about electromagnetic waves is they both behave like magnets as well as electricity. And then finally, we have something called matter waves. Now, matter waves refer to the behavior of many subatomic particles such as electrons, protons, and neutrons, at which times they behave like waves, and other times like particles. And this is the more unexpected and kind of bizarre things. We don't usually think of electrons, protons, and neutrons as anything other than particles, but they do have a wave nature, which means that you, since you're made up of these things, also have a bit of a wave nature, which is a really, really unintuitive concept to say the least. So here's an example. What we have here is a stream of electrons. So this is similar to what would happen, what you would get in an old style television or CRT, which stands for a cathode ray tube. So here are a bunch of electrons going through two openings in a barrier. What you would expect is that on the other side, you should get a buildup of electrons here and a buildup of electrons here. Because after all, if they're particles, you'd expect them to go through this opening and you'd expect a bunch to hit here and a bunch to hit here and get nothing there, and nothing in between. But that is not at all what happens. And what's very strange is they behave like interfering waves. And they produce a series of bright spots, nothing, bright spots, nothing, bright spots. And this is an interference pattern which is normally associated with waves. So here's a model of what this looks like, is you get this pattern. So this here is where the electrons are hitting the screen, and here are the parts where we have low hits. So sometimes you can see a few hits here and there. So they are behaving like they're particles, but mostly from a probability point of view, they're hitting these little regions here, which is really an unexpected property of these particles. But that's more a little bit beyond the scope of the course. We're going to be just sticking with mechanical waves for the most part, and maybe a little bit on electromagnetic waves. So let's focus on the types of mechanical waves, and specifically, we're going to look at first something called a longitudinal wave. So a longitudinal wave, this is a type of wave where the disturbance of the wave is in the same direction as the motion of the wave. So this means if we have the oscillation going back and forth, the motion of the wave is also in this direction. An example of a longitudinal wave would be sound. Sound behaves like a longitudinal wave, and this is kind of a bit what it looks like. So here we have something that models a speaker. So as you can see, we have this thing here, and this is called the baffle. And what you notice is that you can see a wave front moving from left to right. So as we're moving here, you can see it here, 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 here. So the wave looks like it's moving to the right, but behind it, it looks like the waves are kind of moving to the left a bit. Well, in fact, it looks like if you're not paying close enough attention, it looks like the particles are kind of moving from left to right. But if you focus on any single particle, they're just oscillating back and forth. And you can see a couple of red ones that are highlighted here. Look at this red dot. It's just moving back and forth. It's not moving from left to right all the way across, just back and forth. Same with this dot over here, just back and forth, back and forth. Same with this one here. Now, it doesn't matter which one. Take any one of these dots. And you can see if you focus on any one of these dots, they're just vibrating back and forth. Take this one down here, back and forth. Not expected behavior at all, but this is how waves transmit. So this is an example of a longitudinal wave. Now, when we talk about a longitudinal wave, all waves have a cyclical pattern to them. They repeat. So if we take a look, we have a couple of spots here. So if you look where I put these red lines here, the distance between these red lines is the distance between these areas of high concentration. Now, these areas of high concentration, we call those compressions. This distance between those compressions, we call those the wavelength, right? And the symbol we use for wavelength is this Greek symbol called lambda, right? And that stands for wavelength. Now, the wavelength can be measured from your compression to compression, or you could also measure the wavelength between rarefaction and rarefaction. And what is a rarefaction? What's the opposite of a compression? Compressions are areas of high pressure, but in the middle we have areas of low concentration or low pressure, and we call those rarefactions, right? Rarefaction has the root word rare in it. So let's take a look here on this diagram here. So the compressions, again, are the areas of high pressure. So these, or high density, are the compressions here. And in between them are the rarefactions. And as you can see, the root word is rare. It means that the medium is sparse, low density. And those right there are the rarefactions. And I've have a different version of the same thing here. So for the distance between the repeating cycle, that is referred to as the wavelength. And there is that Greek letter lambda. And this is actually a physical length that is measured in meters, right? So this is an actual measurement. So if you were to actually see a sound wave, you could actually measure the distance between these compressions, adjacent compressions, as well as the distance between adjacent rarefactions. Clean that up a little bit. The other common type is something called a transverse wave. Now, transverse means to move across. So this type of wave, the disturbance is perpendicular to the direction of the wave. So these are examples of these, I should say, are water waves and what we see in stringed instruments such as guitars. And they look a little something like this. So there is an example of a transverse wave. So as you can see, the medium is moving up and down, but the wave energy is moving from left to right. And you can see the wavelength is measured between repeats in the cycle. So the wavelength in this can be measured from the top parts of the wave, and we call these top bits up here, we call those crests. Or you can measure them from the bottom parts of the wave, and we call those bottom parts troughs. So either crest to crest, trough to trough, or every other equilibrium point. And I'll show you what I mean by every other equilibrium point. So let's take a look at this example over here. So here in this wave, these things here, these little dots that I'm drawing, these are your equilibrium points, all right? Which means that the wave is crossing the equilibrium. So the top parts of the waves are called the crest. So you can find the wavelength. And again, the wavelength is a measurement of the distance between repeats in the cycle. So we either measure them from crest to crest, trough to trough, or every other equilibrium point. And the reason why it's every other equilibrium point, if we take a look here, from here to here, that's only half the cycle, because the whole cycle consists of this. That is one complete cycle. And the wavelength is the distance for the entire cycle. And here's another example of how these transverse waves move in space. So here we have a mechanical wave, and you can see that it's moving kind of from left to right here, but the disturbance is in the vertical plane. And light waves, they're doing the same sort of thing. The difference is with a light wave, electromagnetic wave, you have the electrical component and the magnetic component. Where with a mechanical wave, this is actually like a physical thing, like a string or water vibrating up and down. Now, torsional waves. Torsional waves, we don't talk about these ones as much, but these are waves associated with twisting. So they have to do with any type of elastic medium that can bend back and forth. A famous example is the collapse of the Tacoma Narrows Bridge back in 1940. The bridge was only up for a couple of months before it collapsed, and as you can see in these pictures here, you can see that the bridge is twisting as a result of a fairly steady wind. It wasn't exceptionally high wind, it just was a steady wind, and it happened to hit a very sweet spot frequency, which caused the bridge to eventually collapse. So they kind of look a little bit like this. So you can see that this type of wave involves a twist in the medium. And you can sometimes see this type of wave evidence during an earthquake. And I've been trying to find pictures of it, but back in 1993, I think it was, when San Francisco was hit with the last major earthquake to hit the city, there was in a street where the buildings were twisted along the pathway. After the earthquake, the wave was frozen. You could actually see this torsional wave distortion occur in the land. It was really quite a sight to see. So let's talk about some equations to describe this. So I have mentioned something called a wavelength, but I haven't really talked about something called frequency. Well, the frequency is defined as the number of cycles over time. So the frequency of a wave has to do with how many times it completes one of these cycles per second. So let's go back to this. So when we look at this, we're looking at one cycle here. We're trying to figure out how much time it takes for one cycle to complete. So if we look at this example here, the time it takes to go from here to here. So again, one cycle and that time to go from that point to that point. The frequency is defined as the number of cycles over the time it takes to complete those numbers of cycles. So here this would be 1, 2, 3, 4, 5. So in this case, the frequency would be one cycle over 5 seconds, or 0.2 hertz. Now, to give you some context, the human hearing goes from a range of 20 hertz at the very lowest. So the lowest frequency that we can hear as a sound, as a tone, is 20 of these vibrations per second. So much, much higher than this. All the way up to 20 kilohertz. Well, 20 kilohertz, that is 20,000 vibrations per second. In North America, our power system operates at 60 hertz. So sometimes when you're plugging in speakers onto a stereo system, or you have a bad connection, you'll hear a buzzing or a humming sound. Well, that buzzing or humming sound we hear is 60 hertz in North America. In the rest of the world, particularly Europe, that buzzing sound is actually 50 hertz, so it's a slightly different frequency. So here, our electrical system vibrates at 60 cycles per second, and in Europe, that is 50 cycles per second. Next concept, the concept of the period. So frequency is what is the reciprocal of something called the period. Now, the period is the time in seconds to complete one single cycle. So let's take a look at an example. Let's say the period was 2 seconds. So that is how long it was to take a single cycle. The frequency would be equal to 1/2, which is equal to 0.5 hertz. So the idea is the period is basically the opposite of the frequency. The period is how long it takes to complete one cycle, and the frequency is the number of cycles over time, or 1 second. So we have half a cycle per second, which means that it takes 2 seconds to complete a full cycle. So the period and the frequency are the reciprocal of each other. So let's take a look at what happens if we have a frequency of 60 hertz. So the period is equal to 1 over the frequency. So in this case, for a 60 cycle wave, it is one cycle takes 1/60th of a second, which makes sense because 60 cycles happens in 1 second, so each cycle could only take a 60th of a second. And finally, the third equation, which is the universal wave equation, which is the speed of a wave is equal to the frequency times the wavelength, where v is the velocity. Well, technically that should be speed of the wave. Frequency, f is the frequency in hertz, and lambda is the wavelength in meters. So let's take a look at an example. Well, a couple examples here. So a wheel rotates 120 times in 30 seconds. All right, so to find the frequency, that's going to be 120 cycles over 30 seconds. So that is 4 cycles per second, or 4 hertz. So now let's take a look at an example of the universal wave equation. A radio wave has a wavelength of 2.887 meters. All right, so that is our lambda. So we want to know what the frequency is. Well, we need to know one other thing, and that is the speed of a radio wave. Well, the speed of a radio wave is the exact same as the speed of light, which is 3 times 10 to the 8 meters per second. I'm going to give you a little bit of context of how fast that is. 3 times 10 to the 8 meters per second is 30,000 kilometers per second. To give you a little bit of context, the speed of sound is about 340, give or take, 347, around there, meters per second, depending on the temperature. So imagine you're at a concert at the JLC. Well, I guess the Budweiser Center, but I always call it the JLC. And imagine that you're on the floor and the artist is obviously on stage and you're at the back of the floor section. So you're a bit of a distance away from the stage. You're watching the concert live. So the performers are performing, obviously, singing into the microphone, and the sound goes to the big program speakers at the front. We call those the mains, and the sound waves come towards you. Well, imagine that concert is also being simulcast worldwide via satellite. So imagine the signal from the microphone being split 2 ways. Once going to the amplifier to the speaker system, and the other one goes to a radio transmitter, which sends a signal up to a satellite. Now, that satellite is located about 37,000 kilometers above approximately Ecuador, Colombia. That far south and that high. So from London, we're looking at a shot of about 42,000 kilometers. Then it is bounced to a second satellite, which is, say, over top of that's over top of Europe. Then that signal is bounced down to, let's say, a radio station in Rome, and then the radio station rebroadcasts that over the air. And one of my relatives in Rome is listening on headphones on the radio. The speed of light is so much faster than the speed of sound that my cousin in Rome will hear the sound of the singer in their headphones before the sound wave from the speakers hits the back of the JLC. That is how much faster the speed of light is than the speed of sound. A radio wave can travel up to a satellite, to another satellite, down to Earth, to another transmitter, well before that sound wave hits the back of the auditorium, which is remarkable. A radio wave can actually circle the Earth 7 times in a single second. That's how fast it is. So, pretty remarkable stuff. Speed of light is quite quick. So, it also should make you appreciate that when something is a light year away, and I just described how fast light goes, you know that that is very, very, very far away. Okay, so let's take a look at this question. So we have V is equal to F lambda. This is a universal wave equation. So we have to isolate for the frequency. Well, in order to do that, I have to take my lambda and I have to divide both sides by lambda. So I'm going to get V over lambda is equal to the frequency. Substituting in, I get 1.039 times 10 to the 8 hertz. Well, that actually turns out to be 103.9 times 10 to the 6 hertz. Now, the reason why I convert it into this non-standard scientific notation, because 10 to the 6 stands for a megahertz. So this is 103.9 megahertz, which I believe is a country radio station that broadcasts out of Woodstock, Ontario. So 103.9 megahertz. And the physical wavelength in space, if you could actually see it, is 2.887 meters apart. Now, fun fact, the FM dial goes between 88 megahertz and 108 megahertz. Now, the center of this is, and this is the most prime real estate, 100 megahertz. And that's about the prime real estate. The center isn't exactly 100 megahertz because obviously it doesn't work out that, but this is the most prime frequency. Now, the reason why is that most antennas are cut to this particular frequency. Well, at 100 megahertz, the wavelength is equal to 3 meters. Now, the most simple antenna is equal to the length of a simple antenna, like a wire antenna, like on the old radio where you actually pull the antenna up, is 1/4 of that wavelength, which works out to about 0.75 meters. And if you look at old cars that used to have the big metal antennas on the cars themselves, they were about 0.75 meters long because they were cut to pick up radio stations around the 100 megahertz range. And that's why old school cell phones, like I'm talking old school cell phones from like the 90s, they used to have an actual physical antenna on them. And the reason being is that old cell phones used much lower frequencies, which had longer wavelengths, which meant that they needed a physically longer antenna. Modern cell phones use much higher frequencies. So as the frequency goes up, the wavelength goes down. So on your new modern phones, the antennas are built inside. And as a result, you don't see the antenna, but there is one. So again, if we look at this equation here, frequency is proportional to 1 over lambda. So as lambda increases, frequency decreases, or the other way around. As frequency increases, the wavelength decreases. So high frequency signals have very small wavelength. Low frequency signals have very long wavelengths. All right, so let's do a couple more sample problems here. So the power system in North America runs at 60 hertz. This means that the alternating voltage completes a full 60 cycles per second. How many cycles occur in 1 hour? All right, well, let's do this. So first of all, we know that the frequency is 60 hertz and the time is equal to 1 hour. The problem is that's the wrong unit. We have to convert that to seconds. That works out to 3,600 seconds. All right, so we want to know how many cycles occur over an hour. Well, frequency is equal to the cycles over time. So to get the number of cycles, that's equal to the frequency times the time, which is equal to 60 times 3,600. So that works out to 216,000. All right, let's take a look at example number 2. A speaker is producing a 2 kilohertz sine wave. Determine the period of the wave. All right, so our frequency is 2 kilohertz, which is equal to 2 times 10 to the 3 hertz. We're looking for the period. Well, frequency is equal to 1 over period, or if we isolate for the period, that's frequency times period equals 1, or period is equal to 1 over the frequency. The period is equal to 1 over 2 times 10 to the 3, which is 5 times 10 to the negative 4 seconds. All right, and finally, let's take a look at example number 3. A string below is oscillating at 4.5 hertz. We want to figure out what the speed of the wave is. All right, well, I know that this distance here is 20 centimeters. So what we need to do is we need to figure out, for question 3, we got to figure out what information we have. So far, I know the frequency. So the frequency is 4.50 hertz. But that's all the information I have. Well, not exactly. In order for me to be able to solve this problem, if I want to find the speed of the wave, I need both the frequency and the wavelength. So I need to look at this diagram here because I know that this distance is 20 centimeters, but I need to know what it is for a single wavelength. Well, let's take a look. So from here to here, that is 1 cycle. So every other equilibrium point. So from here to here, that's another cycle. So that's 1 wavelength, that's another wavelength, and here, well, this is only half a cycle. So we have a total of 1, 2.5 cycles. So what I know is that 2.5 wavelengths is equal to 20 centimeters. So lambda is equal to 20 divided by 2.5. And that's equal to 8 centimeters, except that's the wrong unit. We have to convert that to meters, which is 0.08 meters. So our wavelength is 0.08 meters. So V is equal to F times lambda. So that's 4.5 times 0.08, and that is equal to 0.36 meters per second, or 36 centimeters per second. Next concept, the transmission of waves. So we're going to talk about waves traveling on a single medium. An example would be something on like a string. So here are some interesting concepts about waves. A passing wave will cause a temporary disturbance within a medium, which means that it's only a temporary deformation of what the medium looks like, after which the medium returns to its normal state. The speed of the wave is dependent on the medium, and these are, again, we're talking about mechanical waves. For electromagnetic waves, the speed is affected by the medium that it's going through as well, but electromagnetic waves don't require a medium, so when they go through space, they travel at the speed of light, which is the fastest they can go. Traveling through different things like air or glass, those waves do slow down, but electromagnetic waves travel at the speed of light. Mechanical waves vary quite a bit. So some factors that affect wave speed are the density of the medium, the rigidity of it, right, how stiff the medium is, the state, whether it's liquid, gas, or solid, and the viscosity. What is really unexpected behavior is what happens when two waves are on a collision course. When we have two particles, imagine we have two objects about to collide. When two objects are about to collide, when they collide with each other, the path of both objects are going to be interrupted by the collision. So just think of playing a game of billiards, or if you prefer the word pool. When one billiard ball hits another billiard ball, both of those objects change their direction. With waves, something very different happens. When two waves are on a collision course, they will pass through each other without any permanent effect on either wave. At the point of collision, though, the amplitudes of the two waves will mathematically add to form a temporary wave called a superposition. So when that occurs, we have these effects known as what's called constructive and destructive interference. So the best way to explain it is to show it. So let's take a look at what we got going on here. So we have two waves. This wave here is moving in this direction, and this wave is moving in the opposite direction. So these two lines up here show what the waves would look like as if the other wave wasn't there. So this flatter pulse is moving along its own line here. This pulse here is moving to the left along its own line. But this down here represents what would happen if they were traveling on the same medium towards each other. So let's watch what they do. And right there, notice what happens with the wave here. At this point, if you look, and let's follow this line, this is the equilibrium. So that's a 0. And if we look at this wave up here, that's a +2. And if we take a look at this wave over here, that's a 0. And up here is a +2. Well, the waves literally mathematically add. So if we have a +2 and a +2, we combine those two together, we should get a +4, which is precisely what we get. 1, 2, 3, 4. Now let's take a look over here. If we look at this part of the wave, this is 0, this is 1. 0 plus 1 is 1, and we have 1 right there. And if we look over here, so this is a little over 1, and over here we have an amplitude of 2. So 1 plus 2 is 1, 2, 3. So the two waves mathematically add to produce a new wave that is just a mathematical addition of these two waves. But then they pass on past each other as if no collision occurs. So watch it again. So when the wave, and then once the waves are done, they pass by each other as if the collision never occurred. And that, what we see here, is a type of interference. And we call this interference constructive interference. Now let's see why we call it constructive interference. Well, constructive interference implies that the two waves work together to build a larger wave. To construct, that's where the constructive is. They work together to build something bigger. Well, the opposite of constructive interference is something called destructive interference. So let's take a look at an example of destructive interference. So here are our waves moving along. Notice in this case, this is our positive wave, but this wave here has a negative amplitude. And focus on this point right here. Notice the amplitude stays 0 here. And what you can now see is the effect of what is called destructive interference. This had an amplitude of +2. This here has an amplitude of -2. So we got a +2, we got a -2. So +2 plus -2, that equals 0. And that's why we have our destructive interference. Here the waves work against each other. They cancel each other out. And there you can see it again, destructive interference. Well, I actually have examples of that occurring in real life. So let's take a look at constructive interference. All right, so now in slow motion, you can see that when these two pulses meet, the amplitude right there got very large. So that is our combined amplitude of our wave. But as you can see, the original two waves, so look at the amplitude of this wave here. The amplitude of this wave is about that big, and the amplitude of the other wave is about that big. And when they combine, we get constructive interference. Now let's take a look at some destructive interference. So when we look at destructive interference, and of course the waves happen very, very quickly there, so we're going to slow it down. So when we go into slow motion, you can see that this wave on the left is a negative pulse, this wave on the right is a positive pulse, and right around here, right around this region, if we focus on that, you can see the destructive interference. Look at the wave heights. The wave is now smaller than the individual waves were before. They cancel each other out, and here the amplitude stayed near 0, and then the wave passes through. So that is an example of destructive interference in real life.